back from that short break. We're now going to have a bit more of a look at the relationships between frequencies and wavelengths in electromagnetic radiation. So let's jump back to our concept map and see where we're going. We've been talking about electromagnetic radiation. As I said before, we've already unpacked how it behaves like a particle and a wave. We've broken down this idea of it propagating as an electric and magnetic field through a vacuum. We've related that propagation to its speed, and we've now been recently looking at how the spectrum of electromagnetic radiation is made up of different frequencies and different wavelengths. But the question remains, is there a mathematical relationship between the frequency, the wavelength, the period, and even the energy that we've been discussing in part of these electromagnetic waves? Well, let's have a look. Our question asks, are there patterns or mathematical relationships between the wave's speed, wavelength, frequency, and period of our electromagnetic wave? So let's have a look at one of our diagrams from earlier and see if we can get a feel for the pattern or relationship that might be present. So this is the combined diagram from earlier that shows the frequency and wavelengths of different types of electromagnetic radiation. You can see here on the left-hand side we have our AM radio, widely regarded as the lowest energy with the lowest frequency and the highest wavelength. And over here on the right, we have radioactive elements which we said produce our gamma rays. Here you can see they have by far the smallest wavelength and the highest frequency. So if we look at the entire spectrum as a whole, we should be able to see quite a clear trend. The frequency from left to right, from radio waves to gamma rays, is increasing and does so quite dramatically, while when we look at the wavelength, we can see that the wavelength increases when we move from the gamma ray side of the spectrum to the AM radio wave side of the spectrum. Can we reinforce this relationship that we seem to be observing using a mathematical statement? Absolutely we can. But to do so, we're going to have a look at the wave equation. Here in the wave equation, we already know that the velocity of a wave in meters per second can be calculated by taking the frequency of the wave in hertz and multiplying it by the wavelength in meters. But this isn't the version of the wave equation that we usually use for electromagnetic radiation, is it? No, we need to replace the velocity value with the velocity that all electromagnetic radiation travels at through a vacuum. That's speed of light, the symbol c. We already know that all electromagnetic radiation travels at the same speed, c. This c is 3 times 10 to the power of 8 meters per second, an extremely high speed. And it is called the speed of light. And it changes when substituted here for the velocity, our wave equation to state that c for an electromagnetic wave can be calculated as the frequency of that electromagnetic wave multiplied by its wavelength. But with this version of the wave equation, we don't yet clearly see our mathematical relationship between the frequency and the wavelength. So to see it, we need to manipulate the formula a little bit. Remember that c in this context of electromagnetic radiation is constant. And therefore, we can rearrange our formula with very little worry about what happens to c. If we take our formula number 1 here at the top, and we divide both sides by the wavelength, you can see that we get this expression, which says that the frequency is equal to the speed of light divided by the wavelength. We could have also divided both sides of our equation 1 by the frequency to get that the wavelength is equal to the speed of light divided by the frequency. What is the significance of this manipulation? Well, it allows us to clearly see that frequency is inversely proportional to wavelength, and wavelength is inversely proportional to frequency. What does this mean? Well, this means that for electromagnetic radiation, as the frequency of the radiation increases, its wavelength tends to decrease. Having a look at this quick diagram, we can clearly see that if we take the distance from two consecutive crests on the wave at two different points, we can see that the wavelength is changing based on the frequency. Higher frequencies generate much smaller wavelengths. And this relationship is going to have a big impact when we try to understand the energy associated with electromagnetic radiation. So, from that little GIF, we were clearly able to see that as the frequency of the electromagnetic radiation increased, the wavelength got smaller. But what happens to the frequency when we change the wavelength? Let's have a look. Here in this GIF, you can see that the top wave has quite a bit smaller wavelength. And the bottom wave has quite a bit higher or larger wavelength. Now notice the numbers on the screen. See how many complete waves pass per unit time. We can see here, as the GIF restarts, that almost a full 4 waves of the top electromagnetic wave pass before a single wave of the lower electromagnetic wave passes. We can clearly see again that as the frequency of the wave increases, the wavelength gets smaller. And as the wavelength gets bigger, the frequency gets smaller. So let's practice some of these ideas as a question. In this question, we are asked to calculate the period, given the symbol T, of yellow light. And this yellow light, we are told, has a very specific frequency, 5.16 times 10 to the 14 hertz. A very large number for sure, but we need to get used to working with large numbers when we work with the electromagnetic spectrum because the frequencies tend to be very high. So to calculate the period of our wave using its frequency, we're going to have to use the formula that we have seen already that relates the period of a wave and its frequency. We know that the period is inversely proportional to the frequency of the wave. Also, it's important to recall that period is measured in seconds and frequency is measured in hertz. So to perform our calculation, we already have our formula. All we need to do is substitute the frequency value that we have, 5.16 times 10 to the 14 hertz, and then put it into our calculator. All right, so to do our calculation, we're going to have to substitute our frequency. We've got 1 divided by, in brackets, 5.16 times 10 to the power of 14. Make sure to close our brackets and then hit equals. We can see that the period of this yellow light would be 1.937984496 times 10 to the minus 15, which we are comfortably able to round off to simply 1.94 times 10 to the minus 15 seconds. Now that's an extremely small period. 10 to the minus 15 seconds is fewer in scale than a billionth of a second. So what does that tell us? Well, it tells us that the frequency of this light is not only very high, but the time it takes for each wavefront to pass a particular point is extremely small, a smaller amount of time than most of us would ever really be able to understand. Returning to our concept map, we now have a good understanding of the spectrum of electromagnetic radiation and how this spectrum is made up of different frequencies and, because of the mathematical relationship we just unpacked, also different wavelengths. Let's take a short break and then come back to unpack these ideas a little bit more.